if we've got a nonpolar covalent bond, we have a molecule that's formed, and there's no area of charge on it. Okay? There is no area of charge on it. In a polar covalent molecule, even though these things aren't ions, they have areas that have charge, partial charge. And in your book, that's shown with a little delta sign, delta plus, delta negative. You may have seen the graphic on page 163. So if we look at a chlorine let's look at a chlorine and oxygen bond. Now let's look at the sulfur hydrogen. So hydrogen sulfide is something we commonly see. Oops, I'm going to steal your marker.
Stinky.
Yeah, hydrogen sulfide is stinky.
Where your marker is at already.
That's the rotten egg smell that we're all familiar with. And we're not going to do this really by the book, but we have 2 hydrogens and 1 sulfur. And the sulfur is going, what's the sulfur's electronegativity? If you look on page 151, sulfur's electronegativity is 2.5. Okay. Hydrogen's electronegativity is 2.1. So what's the electronegativity difference? So let's jot these down. Sulfur, En equals 2.5. Hydrogen, En equals 2.1.
0.4.
What's the difference? 0.4. 0.4 En difference. So, based on that difference in electronegativity, what kind of bond would you expect to form? Polar covalent, just a little bit,
Yeah.
but it's polar covalent. Which one of those is more electronegative? Sulfur's got a higher electronegativity value. So based on that, when these two form a compound, sulfur is going to suck up more of the electron cloud. Okay? And actually this molecule ends up looking, let's do a slightly better job representing this. Sulfur ends up sucking up more of the electron cloud. Sulfur ends up with a slightly negative end and a slightly positive end. Okay? Looks a lot like Mickey Mouse. Looks a lot like water. There's a reason for that. We'll talk about that more later. That's a polar molecule. There are areas of distinct charge. We can look at the individual molecule and we can say, oh yeah, this is the negative end of the molecule. This is the positive end of the molecule. Okay? And polar substances behave in particular ways. We'll talk a lot more about that as we go. If we have something like, well, oil is a great example of something that's non-polar. So cooking oil, vegetable oil, olive oil, soybean oil, corn oil, all of those are non-polar. So's gasoline, so's diesel fuel. Those are all non-polar. But let's look at a simpler non-polar. Okay, chlorine, bromine. Chlorine and bromine can form a compound. And what's the, so on page 151, look up, page 151, what's the electronegativity for bromine? What's bromine's electronegativity? Bromine's a halogen. 2.8. What is chlorine's electronegativity? Pardon? 3.0. So what's the difference in electronegativities there? 0.2. What kind of bond will we expect to form? Non-polar covalent. They're going to share their electrons pretty evenly. So when we look at the electron cloud around the two of them, despite any bad drawing I might do, we're not going to see a big difference. There's no area in that molecule where we can say, oh, this is the positive end, this is the negative end. The electrons are evenly distributed, the electron cloud is evenly shared, there are no areas of charge. Okay? So, if I have a molecule that has an area of charge, what kind of molecule is that? Thank you, Colton.
Oh, sorry.
That's okay. I know. I had
We had no clue.
It was a good assist.
I just saw you.
We'll call that an assist. Okay. Oh yeah, that's okay. So if we've got areas of charge, it's a polar molecule. Like the poles of a magnet. Like the poles of the Earth. The poles of the Earth are north and south. The poles of a polar molecule are positive and negative. Okay, make sense? All right. Let's get rid of this all our stuff here. So if I give you